Okay, up on tap for today is study assignment A, which a reminder that your study assignments can actually be found in your lab manual. They are after all the real experiments. Then a bunch of study assignments come through. They're basically like worksheets. And today's is really study assignment A, which is about really kind of conversion, significant figures, all that stuff that we talked about previously is really like a pre-chapter in your book. I think they call it like a review chapter before chapter 1 in the actual textbook. So what I'm going to do today is kind of take some time and we're going to go over some of the basics of everything that's in that review chapter. Maybe not every little inch or not a lot of examples, but hopefully just to make sure everybody's on the same page in terms of measurements, also in terms of significant figures and how to do conversions, dimensional analysis, how to show your work, and also density. So we're going to go over some of these things again. Hopefully, most of it you're familiar with, and at least I'll feel better that everybody again is on kind of the same page in terms of this stuff. Again, if you want to sort of review or look at this information in the textbook, it again is kind of a pre-chapter to it, to the actual book or chapter 1 there, and you could reference it. With that being said, when we're done with this, we will talk about a couple of things on the study assignment specifically, just to make sure people follow instructions. And then we will talk about the experiment that's coming up here on Thursday, which is experiment 6, which is our first formal experiment. And we'll talk about again everything that you need to kind of have done before you arrive on Thursday to do the experiment. So we'll take a look at that, and then we'll do a few other reminders like exam next week, right? So we got a few of those things to talk about. So we're going to start with this. And like I said, just kind of an overview of a lot of those topics. Again, hopefully it will kind of jog your memory or that everybody will be hopefully on the same page. So let's just kind of get into it here. I'm just going to kind of freehand it here. I don't really have notes per se, but I hopefully remember most of it. So let's talk about measurements, obviously, as well, since we are obviously in a lab and measurements are really important. Whenever we do take measurements, right, it is always important to have both a number and a unit. Remember that if you just write a number like 100, it really is useless because it gives no reference of really what it means, right? I could have $100, which would be great. I could have 100 pennies, still not bad. But maybe I have 100 apples, which if you like apples, I suppose is not a bad thing as well. So really, you should never, obviously, in chemistry or any time, just have a number. You should have some type of unit that's associated with it. Now, when we talk about units, there are two types of units that you may be familiar with. There are basically the English units, or sometimes people refer to as the US units, and pretty much we use those. And then everybody else pretty much rolls with the metric system, basically, in terms of units. And obviously, as you might have learned, right, that could create some issues. And in somewhere around 1960 or so, they had a conference on weights and measures, which sounds like a great time. But they came up with sort of a standardized unit that's used in science and specifically chemistry, which is sometimes referred to as the SI unit. And that's the International System of Units. Truth be told, that's kind of like your metric unit for the most part, kind of one. So sometimes you'll see SI units. And obviously, it's important when you talk about units that you understand what those units mean, right? So common units say a mass, right, or grams and kilograms. A common unit of volume are liters, milliliters, cubic centimeters. Also of length, right, or distance, meters, centimeters, kilometers are common units. Time is seconds, right? So it's really important to have an understanding, again, hopefully you do, of, when you see a unit like grams, it's referring to a mass and not a volume. So you don't tell me I had 54 grams of volume, right, in my graduated cylinder or anything like that. Now, just as important as the units is also the measurement, and taking proper measurements is really important. So whenever you take a measurement, there is always some degree of uncertainty associated with that measurement. So for example, if you got like a 1 there, and a 1, 2, 3, 4, 5, 6, 7, 10, a little ruler action happening, maybe centimeter, and you got like an arrow, maybe like there. Whenever you use any piece of equipment, there's always going to be some degree of uncertainty. That degree of uncertainty will depend on the piece of equipment. There's usually two numbers that you want to look at: the large markings that usually have actual numbers, and you want to look at the small markings that are the kind of dashes between those numbers. So in this particular case, our large marking is 1 and 2 centimeters, which means each of the large markings do represent 1 centimeter in this case. You then would want to count the small markings between the two large markings. You always want to start counting after the previous large marking. So that's 1, that's 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 markings between a 1 centimeter difference. That means each marking represents how much? 0.1 of a centimeter. Not everybody at once. Yes, 0.1 centimeter there. That's like 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2. So whenever you take a measurement, there should always be some measurements that no matter who looks at it, everybody should agree. Everybody should at least agree with my arrow here that it is at least 1.4. These are what are sometimes referred to as all the certain numbers. Now, it's not exactly 1.4, it's not exactly 1.5. That is where we get the estimation or uncertainty in this measurement. I may look at it and go, I think it's like halfway there. And I may record a 5 along with my units. And this would be my first uncertain number. Now, somebody else may look at it and go, I think it's a little short of half. Maybe it's like a 4, or maybe it's a little past half. Maybe it's like, a 6. You should always, when you take a measurement, figure out how far you can take the reading to. And you should always record all the certain numbers and the first uncertain number. Because when you do that, those are everybody's favorite thing, known as significant figures, by the way. Yeah. That is where sig figs come from, by the way. That is then means that this guy has actually 3 significant figures. The uncertainty lies in this case with the 5. Maybe it's like plus or minus, up 1 or down 1 in that particular case. Now, again, it's really important to always look at the piece of equipment, because not all scales are the same depending on the piece of glassware that you look. As you know from your Kool-Aid example, when you actually pulled out the graduated cylinder and put those beakers away, and you got 10, you got 20 milliliters here. We put a little volume of our red Kool-Aid in there, for example. Here we would want to look at our scaling, and again, our large markings is 10 and 20, which means we have a difference of 10 milliliters in this particular case. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings between those two numbers, which means each of the small markings in this case actually represents 1 milliliter. 10 divided by 10 is 1 milliliter, right? That means this guy's 11, 12, 13, 14, 15, 16, 17, 18, 19. And of course, we know, right, when we take a reading, we want to read from the bottom of the meniscus, right? and we will always get this sort of curvature, which is known as the meniscus. The curvature occurs, as we will learn later on, but maybe you also know, is because the liquid in contact with the glass will rise up the walls of the glass through capillary action, because the attractive force between the liquid and the glass is actually stronger than the attractive force between the liquid and itself. So the sides that are touching the glass start to come up. That's why in this case we read from the bottom of the meniscus where it is not touching the glass, because without that attractive force, that's actually where the volume is. Meniscus is also why beakers are crappy pieces of equipment to measure with, right? Because it's a big opening, meniscus is spread out. You think you're at 100, you're nowhere near 100, right? Maybe again, some of you found that out the other day when you were measuring things out. So again, you always want to make sure that you do use the proper equipment when you're doing that. Once again, when we look here, we can see that it is at least 14. Once again, we see that it's not exactly 14 or 15. So we do need to record 0.5 milliliters, this being again our certain numbers, and this being our first uncertain number. And again, that would then mean that this guy also has 3 significant figures in this particular case. Once again, when you do look at scales, even if you're using the same graduated cylinder, it may have some different markings. So for example, if we had this guy, and we'll put a little bit of that right about there. In this case, our large markings on this particular equipment is 10 milliliters. There is 1, 2, 3, 4, and 5 markings between them. That means that each of our small markings in this case actually equals 2 milliliters, right? That means that this guy would be 12, 14, 16, 18. That means when I take my reading here, I am between 16 and 18. What comes between 16 and 18? 17 comes between 16 and 18. Also not a trick question, by the way, yes. That would mean in this particular case, how many sig figs would that have? 2 significant figures, right? The uncertain number here is the 7. In this particular scaling, you do not have enough distance between these to know where 16 stops, 17 starts, and 17 ends, right? Or we kind of know where 17 ends, but you don't have enough distance to do that because of the spread. In general, you usually could go one more place to the right of the smallest marking. This would obviously be an exception to that. You cannot do that. If you are ever not sure how far you should take the reading, and you can't remember that you usually could go one more place to the right of the smallest marking, you could actually take the smallest marking and divide it by 2, and you get 1. And that's sometimes referred to as the uncertainty in this case. This would be plus or minus 1 milliliter. That's a whole number. That's where you should take it. This smallest marking here was 1 milliliter divided by 2. That's 0.5. That is plus or minus 0.5 milliliters. That's the first decimal place. That's where you should take the reading to. You do it on this one. Smallest marking is 0.1 divided by 2 gives you 0.05 centimeters. That's plus or minus 0.05 centimeters. That is 2 decimal places. That is where you should take the reading to. So if you're not really sure, but you can feel pretty confident on what the smallest marking represents, you could actually just divide it by 2 and it will tell you how far you should actually take the reading to. Any questions on that? Now, stealing this ruler here and changing my arrow. What happens if I have an arrow that goes like dead on the 1.4 marking here on this ruler? I record 1.4 centimeters. I record 1.40 centimeters. Is there a difference in how I record those numbers? Does it make a difference? If you're not sure, let me explain what the difference is. Let's start with what we do know. This guy right here has how many significant figures? It does have 2 significant figures. The uncertain number there is the 4. So when you record 1.4 in this situation, you're saying, I think it's 1.4, but it could be like 1.5, could be like 1.3. That's a pretty big stretch, right? By the way, my mark is like nowhere near either of those numbers. That's a lot of error you just introduced that you shouldn't. And you created a lot more error in that measurement that you really shouldn't have done that. If I record this one has how many significant figures? It does have 3. The 0 is the uncertain number there. You're saying, I think it's 1.40, but maybe it's like 1.41, maybe it's 1.39. That's like right about there, yeah? That's pretty much what we're seeing with this particular ruler. Not a lot of error. Because you have the ability on this particular ruler to go to the second decimal place, you need to put the 0 there. Because if you loft off the 0 and just record 1.4, you made your measurement pretty crappy. Yeah, then it shouldn't have been based on this. So you sometimes do need to add a 0, right, to make it what it needs to be. You shouldn't loft off a 0. By the way, just so you know, if you had something like this guy here, you shouldn't add a 0 either to make it more scientific, because this one now has how many significant figures? 3, which you have no ability to do that on that piece of equipment, right? So adding just to add is not good, because you're now saying your measurement is way better than the ability of the actual equipment, right? So you can't just add if you want, but you do need to add zeros in certain situations to maintain the correct number of significant figures. You shouldn't just add to make it more scientific or anything like that, or chemistry, like they say, I suppose. Yeah. Any questions on that there? All right, so just make sure everybody knows how to take measurements. By the way, does every meniscus go upside down like a U? The answer is no. Some actually go the other way. Very common one is mercury, which you'll never see because it will kill you, and they take an amount of colleges and classes. But mercury actually goes the opposite way, and you actually would read from the top of the meniscus because it has the opposite effect. The attractive force between mercury and itself is actually stronger than mercury in the glass, so it comes in on itself, and the actual volume is actually towards the top. I would say probably 99.9% of the time, that's what your meniscus is going to look like. It's going to look like a U, but there are certain elements and stuff that or certain things that will give a meniscus that goes the opposite direction. All right, so since we're talking about sig figs there, let's talk about official rules for sig figs, right? And again, any non-zero, right, is significant. So if you have 1, 4, 3, 2, that is 4 significant figures, right? It is the zeros that give people a hard time. So let's start with those. The first type of 0 is referred to as a leading 0. Those guys are not significant. So 0.00113, we start left to right. We do not start counting until we hit the very first non-zero, which would be the 1. Then we roll through and we get 3 significant figures in this particular case. The next type of 0 is a trapped 0, or a captive 0, they call that. And those are significant. So those are basically zeros between 2 non-zero numbers, like 4004. If we start counting here, these are trapped, they're significant, and that significant would give you 4 significant figures in this case. The last 0, which screws up everybody most of the time, is the lovely trailing 0. And these are the zeros that come at the end of a number, which may or may not be significant. What determines if it is significant is if there is a decimal point written. Then it will be significant. So if I go 400, I have how many significant figures in that number? I only have 1, right? If I write 400 like this, how many significant figures do I have? I now have 3. These zeros at the end would be significant, right? 0.00400030 has how many significant figures? I have no idea. I was just writing. So let's take a look. We got that's where we're gonna start counting, right? So that's significant. Those are significant. That's 3, 4, 0 at the end is a significant. It is significant because there is a decimal point here, right? So it doesn't have to be near it. So all those guys would be significant. So that is 5, I think I heard, would be significant figures there. The uncertain number are the estimated number. Will it always be the last number written? It will not always be the last number written. It will always be the last significant figure written, right? So if I had something like 12,000, that has how many significant figures? Has 2, right? The uncertain number is the 2, right? The estimated guy there. That is the uncertain number in that case, right? So not always the last one written, but should always be the last significant figure written in that case. Any questions on that there? Now, we talked about scientific notation, and I think we talked about using our calculators when we were doing the first couple of chapters. A reminder that proper scientific notation is n times 10 to the n, where this is a number between 1 and 10. It really can't be 10, but it can be 1, but it can't go above 10. It can't be below 1. And this is either, again, a positive or negative number, depending on which way you're going to move the decimal to achieve that number between 1 and 10. So if I had 4, 3, 6, 2, 1, I would go 1, 2, 3, 4 places to the right. 4.3621 times 10 to the fourth would be the proper way to write a number in scientific notation. If I had 0.005040, I would go 1, 2, 3 places, 5 point, bad 5, 5.0040 times 10 to the negative 3 would be the proper way to write that. Why do I keep all the numbers? Do I need to keep all the numbers? So let's talk about numbers written in scientific notation. All the numbers, when you write it in scientific notation, that comes before the times 10 part are significant. That means that when you have a number like this, which started with 5 significant figures, it needs to keep all those numbers to still have 5 significant figures. This number here has also 5 significant figures. It needs to have all those numbers to have 5 significant figures. That is why in some cases, scientific notation is the only way that you could write a number that a proper number of significant figures. Like if I go back to my 12,000 example, and I want to write 3 significant figures, is there a way to do it without scientific notation? There is not a way to write a number in 3 significant figures without scientific notation, because if I write a $1.20 there with a decimal, it is 3 significant figures, but is it the same number? It is not. If you don't believe me, if I owed you $12,000 and I said, here's 3 sig figs, here's $120, we're good, right? I go buy a pizza with my rest of my money that I just saved there. I'm not going to do well. I'm not going to get to my pizza, maybe. So we never, obviously, speaking of rounding, right? We never want to do any crazy rounding that we change the meaning of the number. So that very often happens when people try to get the right sig figs. They try to round crazily to get the right sig figs, and they end up changing the meaning of the number. So you never want to do that. So there really is no way to do that. We would have to write 1.20 times 10 to the 1, 2, 3, 4. That now will have 3 significant figures in this case, and that's what we're looking for. That is why scientific notation is really important, because you could really control how many significant figures you want by putting zeros or taking off zeros. Like if I only wanted 2 sig figs, I could just write it like this, and now I have 2. If I wanted 4, I add an extra 0. Now I got 4 sig figs. So you can really control how many significant figures you have by using scientific notation. And sometimes it is really the only way to get the right answer. I won't dwell too much on this because I think we've talked about it in those chapters, but obviously exponent buttons, yes. So always a number in scientific notation. Make sure that you are using your dedicated on your calculator exponent buttons when you punch it in, like we talked about. So 4.25 times 10 to the minus 4. Again, 4.25 exponent button. negative button, which again on most calculators looks like this, or looks like this, and 4. And again, that would be the proper way on most people's calculator to punch scientific notation in. Remember that when you do get the answer, which again is a common mistake when you got a bunch of numbers here and it's like E minus 4, don't forget to include the times 10 part. When you do write it as your answer, do not use the E for an answer. Yeah. Write out the times 10 part. Yeah. So if you're given it as your answer, you should write out 4.25 times 10 to the 4 minus 4, not 4.25 E minus 4. Yeah. So we use it for calculators. We use it like on Excel. But if you're given an answer in scientific notation, do not use the E as part of your answer. Use the times 10 part and write that part. Any questions on that? I think everybody's pretty good on scientific notation punching it in. If by some chance you still don't know how to do that, I would definitely see me this week before next week's exam, right? To make sure that you know how to do that. Lastly, here with significant figures calculations, right? So when we do calculations, we want to make sure that we do them to the proper number of significant figures. So there is multiplying and dividing. And when we multiply or divide, we look at the number of significant figures, and your answer should have the same number of sig figs as the number with the least number of significant figures. So if I'm multiplying 425 times 0.1040, this has 3 significant figures. This guy's got 4 significant figures. That means my answer should have 3 significant figures when I'm all said and done, whatever that answer may be. If I'm adding or subtracting, we are looking at decimal places. And it also is the least number of decimal places. So if I had 1.111 plus 2.0 plus 3.2156, and I add that together, 6623356. We are looking at decimal places here. That is 3, that is 1, that is 4. That means we should end up right about there, and we should end up at 6.3. 6.3 has 1 decimal place, but it has 2 significant figures, which is important if you're going to go on and use that in another calculation. I guess I'll pop my other number in there since I got my calculator handy-ish. Oh, 4. So actually, on this one, you get 44.2, which actually works out very nice, right? Now, sometimes you do combo these things, so you want to keep track of what's going on. So if we were doing something like 0.040 times 1246 divided by 1.56, and then add it to 0.45, right? A lot going on there. So we want to kind of keep track of what we would do. Typically speaking in math, things in parentheses we do first, right? So we would kind of multiply here, which is significant figures. So that would be 2 significant figures. That would be 4 significant figures. That means technically speaking, off the top part, I should really end up with 2 significant figures. Should I strictly round right away? I should not, right? You should always wait to round to the very end, but you should keep track of everything that's going on. The next math thing I would do is take the top number divided by the bottom number. That is 2 divided by 3 significant figures. That means really when I'm done with the first calculation, I am at 2 significant figures, right? Gosh knows what that is, but let's see. What's 0.04 times 1246 divided by 1.56? Technically speaking, 31.94871795. That's a lot of numbers. But really, this guy should end right about there, right? At about 32, which is 2 significant figures. Yeah. So If you want to round, you could at this point, because the next thing we're going to do is add, or you can just add it if you want, whatever you want to do. So if I add that to my 0.45, I will end up with 32.3987 and so forth. Technically speaking, where should my number end? This guy really should be two significant figures, which means that is really a whole number, right? So now I'm taking a whole number plus two decimal places. My end result actually should be a whole number in this case. Any questions on that there? Yeah. So that will give you that. Obviously, if you rounded earlier and took the 32 plus the 0.45, you would actually still end up the same spot at 32.45. You would round to a whole number, which would still be 32. So it's really important when you're doing calculations to, again, not really round to the end, because if you round a lot, you will move away from the right answer. And you do want to keep track of it. Some people keep guard digits, some people put lines. I don't really care. I personally have the idea that I usually just keep rolling with my calculator, what number is in there in most cases. But if you do want to write down a number, I would take a few extra digits past where you should end, and that usually will correct any type of rounding error. Any questions on calculations of significant figures? All right, so we did that. Let's talk about our friend temperature scales, right? Just to make sure. There are three types of temperature scales here: degrees Fahrenheit, degrees Celsius, and our friend Kelvin. Degrees Fahrenheit is what we use for our temperature. Celsius is used on every ruler, I was going to say, but how about a thermometer will work? And Kelvin was used to be called the absolute temperature scale. To go between these two are all these things. There's some different ways. I would say most of the time, temperature and chemistry needs to be in Kelvin. Pretty much you're going from Celsius to Kelvin. So the temperature in Kelvin is equal to the temperature in Celsius plus 273. The correct number is 273.15, but most people drop the 0.15. If you like the 273.15, you're more than welcome to keep it, but that is really the true number. That also means if I want the Celsius and I have the Kelvin, I'm going to subtract 273 in that case. I would say probably 9 times out of 10, that's going to be pretty much what you're going to be doing. And probably 99 times out of 100, that's going to be what you're doing, converting it to Kelvin. For fun's sake here, right, if we want to go and get the degrees Fahrenheit, that is 1.8, the temperature in Celsius plus a 32. The temperature in Celsius would be the temperature in Fahrenheit minus 32 divided by 1.8. That 1.8, by the way, is 9 over 5, in case you learned it that way, right? You take 9 divided by 5 is 1.8. When we do temperature conversions and only temperature conversions, significant figure rules don't necessarily strictly apply. We use sort of a general significant figure rule. Like if I had 41.1 degrees Celsius and I want to know what that is in Fahrenheit, I would take my temperature here, take 1.8 times 41.1, add a 32 to it. I would get 1.8 times 41.1 plus a 32 gives me a 105.98 degrees Fahrenheit. The general rule for temperature conversions is if you are just converting a temperature value from one scale to the next, it should look like the original value, which means this value went to one decimal place. That is where you should take it. Oh dear, that's going to be a double round on that one. All right, so that's like a 106.0 degrees Fahrenheit in that case. I need to round up, right? Then I need to round up again. Like a lottery move right there, yeah. Any questions on temperature conversions? I would say Fahrenheit and Celsius, not all that much converting going on with those. It is strictly a lot of times Celsius to Kelvin. By the way, the other important thing is there is no degrees in Kelvin, yeah? So it is just Kelvin, right? No degree sign, no degrees Kelvin. These will not be given to you, so you do need to know how to convert to Kelvin, yes. So make sure you know how to do that and how to convert out of Kelvin. By the way, also keep in mind as we go through chapters, even tricky chapters, where they give you temperatures in Celsius and they want you to give the answer in Celsius. I would say most times you still need to convert it to Kelvin to go into the equation you're using or the formula that you're using to get it done. Any questions on that there? Now, when we do conversions, right, and equalities, qualities are two things that represent the same amount of something but are on different scales, like 12 inches equals 1 foot, right? This is an equality. And from any equality, you can write two conversion factors, which are just fractions. 12 inches over 1 foot or 1 foot over 12 inches. The way that we solve problems in chemistry is everybody's favorite thing, dimensional analysis. That's a fancy way of saying problem solving. That's also a fancy way of saying you need to show your work this way, yes? So this is basically the way you show your work here. Dimensional analysis is the idea that you use conversion factors to basically convert from one unit to the next. So use this as a conversion factor, and that gets you the unit that you're looking for. So it is basically opposites cancel. So you can think of things like fractions, top and bottom. So if you want to get rid of the same unit, you put it in the opposite location to cancel it. We multiply whatever's on top and we divide by whatever's on the bottom. That works to cancel out these units. That is the same thing if we took 2 divided by 2 equals 1. You have unit A on top and unit B on the bottom and divide them. It equals 1. They cancel out. Basically, it's the same idea. So in this case, for example, if I had, 454 inches and I wanted to know how many feet that was, the proper way to set this up is 454 inches. We use conversion factors and dimensional analysis to do this. Again, inches are up on top, which means we need it in the opposite location, which is right there. 1 foot is 12 inches. They cancel. We multiply, which you really don't have to do because that's 1. We divide by what's on the bottom here. We take 454 divided by 12. Gets you this number here, 37.83333, a bunch of 3 feet. We do want to give our answer to proper number of significant figures, which means if you're using dimensional analysis, pretty much the only thing you're doing is multiplying or dividing, which means you're looking at significant figures. Do I have to worry about this conversion factor? I do not. This is what is referred to as an exact number. Yeah. An exact number is a definition or an equality or something that's counted. The note to that is we talked about earlier that there are English units, there are metric units, and there are units to cross over, English to metric, right? Kind of conversions. If you're using any type of conversion factor that came from an English to English conversion, like 12 inches is 1 foot, or you use any type of conversion factor that came from a metric to metric conversion, like 100 centimeters is a meter, they are considered exact numbers. You don't have to worry about it. The only time you do have to worry about it is if you cross over. Yeah, so if you cross over from metric to English, you do have to kind of look at it and see, the conversion factor. So for example, like 1 kilometer is 0.621 miles. We would have to look at this as miles is English, kilometers is obviously metric, right? Which is why your speedometer says miles per hour and also kilometers per hour, right? Because you got to sell them in different countries, right? Depending on where you're at. So we would look at this number, and that significant figures would count. So we wouldn't want to look at that number, and that would have 3 significant figures. But in this case, we don't, which means we default back here. That is 3 significant figures. That means we should end up right about there at 37.8 feet. Yeah, and that's really important. So you should always show your work this way, which is dimensional analysis. You don't have to write out the conversion factors, but you do need to show it. That's what is meant by show your work. Yes, is that type of thing. Any questions on that there? Now, in terms of metric, we also have, by the way, prefixes, right, that we use. And those are things like centi, right, is 10 to the minus 2. Kilo is 10 to the 3. We did our friend nano, right, which is 10 to the minus 9. Again, I can't tell you again how many times people screw these up, right? This is, by the way, 1 times 10 to the minus 2. This is really 1 times 10 to the 3 if you need to punch in your calculator. And that is 1 times 10 to the minus 9 if you need to punch it into your calculator in scientific notation. Clearly still using your exponent button, right? So this is how much there is in the base unit to one of the prefix units. So in 1 centimeter, there would be 10 to the minus 2 meters, which gives you, again, 2 conversions that you could use. And as we did before, for example, 1 nanometer, there is 10 to the minus 9 meters, right? And that is, again, the proper way to do that, which gives you 1 nanometer over 10 to the minus 9 meters. Our 10 to the minus 9 meters is 1 nanometer there. So again, you want to use this correctly. So, if we're going with like 454 nanometers and we want to get meters, again, doing opposite, nanometers is up on top. We would need to use it this way. Again, nanometers would cancel, and we would have this times 1 times 10 to the minus 9, going to give us our 4.54 times 10 to the minus 7 meters in this particular case. Yeah. Any questions on that there? So again, you want to always make sure you do it correctly. I would say it's very common people really don't do it correctly and kind of always do this one backwards. So it's very common people want to kind of do that one in the backwards way. So to make sure you don't do that. Also, if you're going prefix to prefix, right? We do that, but maybe we go prefix to prefix. Maybe we have 454 kilometers and we want to know how many centimeters that is, right? You do need to show that using dimensional analysis. The best thing that ties this together is meters, the base unit, right? And you can find those conversions like we just talked about in the previous slide. Kilo is 10 to the 3. Centi is 10 to the minus 2. So the first thing that would make sense is to take 454 kilometers. And again, we want kilo on the bottom. So 1 kilometer would be 10 to the 3 meters. That would cancel. Now we could go from the base unit to our centimeters. And by setting this up with dimensional analysis, we see meters are up on top, which means that we could then go 10 to the minus 2 meters in 1 centimeter. That way they cancel out. Once again, we're multiplying what's on top. We're dividing by what's on the bottom. And in this case, we will end up with we'll get 4.54 times 10 to the 7 centimeters in this case. Yeah. Again, significant figure wise, exact number, 3 significant figures. That is what we should end up with here in our answer. Question on that there. All right, so you try this one. Let's say I wanted to go 436. I was going 4,360 inches per second. What would be my speed in miles per hour? And if I had, let's see, if I had 3,254 cubic inches, how many cubic centimeters would that be? So take a moment there, give you some conversions. 5,280 feet is a mile. Hopefully you know time conversions, right? And 1 inch is 2.54 centimeters. All right, see what you come up with. Okay, so let's take a look, see how you're doing. So we'll start with the first one. We got a couple of units here going on, inches per second. We really have two conversions. We want to go inches to miles, seconds to hours. We want to set it up dimensional analysis way. So one possible route could be inches to feet, feet to miles, as that will tie you there. And that's what I'm going to do. Hopefully we still remember 12 inches is a foot, as they say. So I'm going to start with that. Again, setting it up like this so we can clearly see where the units are going to help us. Inches are on top. Opposite cancels means we need inches on the bottom and feet up on top. We stop right at this point. We're in feet per second, which is getting us closer to what we want. We then need to get rid of feet. So again, opposite location. That means we need to put the feet on the bottom, miles up on top. The feet will cancel. If I lay it up right here, I'm in miles per second. I'm halfway there, right? I didn't give you these conversions, but hopefully you know these, right? So there are 3,600 seconds in 1 hour. Or you could go step by step, right? In an hour, there's 60 minutes. And in a minute, there is 60 seconds, however you want to do it. I'm going to use the 3,600 seconds. I'm going to go up on top. Is 1 hour. The seconds will cancel. That's going to leave me miles on top, hours on the bottom. We're going to multiply whatever's on top here. We're going to divide by whatever's on the bottom. Go that way. So that's going to be 4,360 times 3,600 hit equals. Divided by 12 hit equals. Divided by 5280 hit equals. I'm sure I mentioned it, but when you have a lot of numbers on the bottom, I would divide by each one individually and then hit equals after each one. You'll get the right answer. If you try to punch all that into your calculator at once, you might get the wrong answer depending on how you punch it in. And if you do all that good stuff there, I think you'll end up with 247.727 miles per hour. Significant figure wise, this is an exact conversion. Don't have to worry about it. That's an exact conversion. By the way, exact numbers have unlimited number of significant figures, which is why we ignore them in calculations. We don't have to worry about them. This is also an exact number, which means this number has how many? 3. That means we should end up at 248 miles per hour, right? Number stays with the top unit. It is one of the bottom unit, right? Any questions on my calculation? Again, showing work means something that looks like this. By the way, you might not think dimensional analysis is a great thing to do to show your work, but it could actually help you in a lot of cases because you might not even know the formula you need to use, but if you just think about what units you got to get rid of and what units you got to end up with, you could actually just do dimensional analysis. It'll do the formula for you, basically, if you set it up correctly. So I highly recommend if you're not familiar doing this or using this a lot, you get familiar very quickly on how to show this work. Yeah. All right, take a look at the bottom one here. That's a 3254 cubic inches. I have an inch to a centimeter there, so I'm going to do a inch on the bottom and a 2.54 centimeter, right? I need to do that just once, twice, 3 times. Yes, I do need to do it 3 times there. 2.54 centimeters is 1 inch. 1 inch. Inches squared, inches cubed takes care of all of them. You just do the conversion once. You took care of just one of them, right? You still got 2 to go. You actually have to do it 3 times. So that is 3,254 times 2.54 times 2.54 times 2.54. Gets you a big old number. That's going to get me 53320. That's centimeters times centimeters times centimeters, cubic centimeters. Yeah. Could also write in scientific notation if you like. Could you also show the work like this, which is 3,254 inches cubed? 2.54 centimeters is 1 inch cubed. You absolutely could, but in my experience, most people never live to actually do that number 3 times. They just like put a cube on the units and don't actually do the calculation. So sometimes it's better to actually see the numbers you got to punch in your calculator to make sure that you do it. By the way, did I need to worry about this conversion? That is a metric to English conversion. Do I need to? That is one of the few metric to English conversions that's considered an exact conversion. 1 inch is exactly 2.54 centimeters, so you actually do not have to worry about that English to metric conversion. Question on conversion factors, dimensional analysis, how to do those things. Foots and furlongs, fortnights. There's a question like that, right? All right. What could be left? I don't know. I say density seems like all that's maybe left. I don't know at this point. Let's talk a little bit about density, right? And when we talk about density, density is mass divided by volume. Volume, if we rearrange it, is mass divided by density, and dare I guess mass is equal to volume times the density. Everybody loves the DMV triangle, right? They're taught all that all the time. Probably not, maybe. That's the DMV triangle, by the way. But everybody loves it. Density is mass divided by volume. Volume is mass divided by density. Thanks for not agreeing with me as well. So mass is volume times density. I'm here to entertain myself. It's okay. So that's a quick way that you can rearrange this. Common units of density, grams per milliliter, right? Or grams per cubic centimeter. By the way, those are both a volume. A 1 milliliter equals 1 cubic centimeter, right? That's a very common conversion. By the way, speaking of volume conversions, 1,000 milliliters is 1 liter, also a very common conversion that's used a lot in chemistry. We get something like a cubic centimeter a lot of times from liquids, not really, but more solids is usually these common units. And if you take like the length times the width times the height of like a cube solid, that's going to give you the volume. These are each measured in centimeters, which is a length measurement for each of those. When you multiply them together, it gives you a cubic centimeter, which is a volume in this case, right? So for gases, as we will learn in this class, when we get to the gas chapter, the units of density are actually grams per liter, are typically the units that we associate with gases. The density of something determines, for example, whether it will sink or float in water. If something is more dense than water, it will sink. Right. If it's less dense than water, it will float. Water's density, by the way, and this is liquid water, is usually 1 gram per milliliter. Density of water does change with temperature. Yeah, so as the temperature changes, it actually changes as well. Water is an unusual substance because its solid version, which is ice, is actually less dense than its liquid version. And that's because water molecules and the hydrogen bonding, when they lose energy, can't get that close together. So they create a lot of open space between the water molecules, increases the volume. Thus, this number gets bigger, the density gets smaller. That's why our ice cubes float, right? When we put it in our soda that comes to the top of the glass and all that good stuff. Also, why if you took a can of Diet Coke and a can of regular Coke and threw it into a tub of water, would they both sink? Would they both float? What will happen? One will sink, one will float. Which one will sink? The regular can of soda, because it has a lot of sugar in it, right? The Diet Coke has like artificial sweetener, so it'll actually float. Good party trick. You never know when you need one. You know, try those party tricks. Also, if you take raisins and like some 7-Up in a glass cup, they'll start dancing around from the bubbles and stuff like that. Also, good party tricks. You need to know these things. All right. So when we do density right, the main thing here, obviously, besides the plugging and chugging, is there's really kind of 3 ways that we can kind of get the volume of an object, right? Obviously, we can take a reading from something like a graduated cylinder and just read the volume. We could do something like this, right, where we take some ruler measurements of a solid and we get the volume. But also very common, especially in density, is volume by displacement, which means if you fill up a liquid in a glass container like a graduated cylinder and have an initial volume, and you drop a solid object in there, the water will be displaced by the solid object, and you will have a final volume. And by taking the difference in the two volume readings, you can get the volume of the object, which is the final volume minus the initial volume. So that's a very common sort of way that you could get the volume of a solid object by just dumping in some water, taking an initial and final reading, and that will give you the volume of that particular object. Any questions on any of that pre-chapter stuff? Yes? All right, so you now should be professionals at that.